has a valuation function, and the objective is to select a set S that maximizes the valuation function, so V of S, subject to the budget constraint. Okay, so the sum of the costs for what he bought should not exceed the budget. Okay, so if V is additive, this is just an abstract problem, right? Well, we're going to consider non-additive valuations here, but apart from that, the problem gets more complicated when the costs are private information. So if the costs are private, now we want to start thinking about mechanisms. So for example, if the items correspond to services offered by some agents, maybe people want to misreport the cost. Maybe people want to report a higher cost because then they may get a better payment. Okay? So the ideal goal is to find the set that maximizes V of S subject to the budget constraint. But given the strategic considerations, plus the fact that this is generally an NP-complete problem, what we are after is to find truthful mechanisms, truthful individually rational mechanisms that are budget feasible and that provide a good approximation to the value obtained by the buyer. Okay? Now, this is a single parameter problem, meaning that every agent is just has just one parameter that is secret information, just a cost. Okay. So by Meyerson's lemma, it suffices to find monotone algorithms. I don't want to define actually what this means, but right now. But what I want to say is that if we did not have the budget constraint, it would be easy to construct exponential time truthful mechanisms by running the VCG mechanisms or something like that. The presence of budgets here makes the problem more challenging, and even getting exponential truthful mechanisms is not an obvious thing. Okay, so let's see what has happened here in this field. This type of questions were initiated by Singer a few years ago, who studied non-decreasing submodular functions. So these are monotone submodular functions. And later on, this was followed up by Chen, Graving, and Liu. And actually, even more recently, this was improved by Jalali and Tardos. So we know a randomized 5 approximation when the valuation function is monotone submodular. And in terms of deterministic algorithm mechanisms, we know an 8.34 approximation. Okay. XOS functions were also studied by this paper. And actually here, the picture is much worse. This paper provided a randomized 768 exponential time algorithm. Okay? And this was the best known. Okay? Just to show you how non-trivial these problems can become when you introduce this budget constraint. So these are not polynomial time algorithms in general. Okay, okay, so what did we study? So we focused on submodular and XOS functions, and we actually studied a subclass of submodular functions which are non-monotone. There has been already some previous work on this, which I will mention right away. And we also have some improvement for XOS functions. Now, for non-monotone submodular functions, I think the cat functions is a very representative example, something that you can have in mind, defined where the value is defined by the weight of a cat in a weighted graph. Okay, so for symmetric, the class that we study for non-monotone functions is the class of symmetric submodular functions. So cat functions, for example, satisfy this property. V of S is equal to V of A delete S. Symmetric sometimes is used to denote dependence only on the cardinality of the set, but in operations research, symmetric submodular is usually defined to mean this symmetry property, that the value at S is also equal to the value at the complement of S. Okay. So as I said, a representative example is the cat functions. If we have a graph possibly weighted, the weight of any cat satisfies precisely this property, right? It doesn't matter if you take S or A delete S, or the complement. Okay? So the unweighted version of cat was studied already by Dobzhinsky, Papadimitriou, and Singer. This was an EC 2011 paper. And there, the best known results were a 564 approximation, which was randomized. And if you want a deterministic mechanism, then you go to 5,158. Okay. Let me summarize our results. So first of all, we start with an algorithmic result, which is a byproduct of the approach we took to designing mechanisms. We get, first of all, a deterministic polynomial time approximation of 2e over e minus 1 for symmetric submodular evaluations. And this, to our knowledge, is the best known deterministic mechanism. There is a better randomized mechanism known. And we also get significantly improved mechanisms for some of the cases that I mentioned so far. So we moved down from 3- and 4-digit approximations down to 2 digits, to small constants. And we also have a small improvement for XOS. We get an improvement by a factor of 3. We go from 768 to 244. So here is a summary of what we have achieved so far. For general symmetric submodular, we improve 768 to 10. If you want deterministic algorithms, then we can get an exponential 10 approximation. And if we know of if the problem admits an LP relaxation with an upper bound on the integrality gap, and rho is the upper bound on the integrality gap, then you get this expression as your approximation. And that's in polynomial time. We pay special attention to the cut functions. So for unweighted cut, we improve these numbers down to 10 and 27. For weighted cut, no deterministic mechanism was known before. We derive a 27 approximation for this problem. So, okay, these results are not tight, but at least we are now down to much better approximation ratios, and some of them are in polynomial time. So for unweighted and weighted cut, we are in polynomial time, and as long as we have LP relaxations with good bounds, we are down to good approximations as well in polynomial time. Okay. All right. So in the remainder of the talk, I want to focus more on the byproduct, because that's what we find to be the most interesting part, actually, of the paper. And it highlights the idea that we used, and maybe this can be useful in other problems as well. So the theorem 1 is an algorithmic result. It's not about a truthful mechanism, showing that there exists a polynomial time 2e over e minus 1 approximation algorithm for symmetric submodular maximization, subject to a budget constraint. Okay, so this is based, the approach is based on a combination of local search for the unbudgeted version of the problem, plus the use of greedy algorithms for monotone functions for the budgeted problem. Roughly what happens is that for submodular objectives, once we identify a local optimum, even for a non-monotone submodular function, once we identify a local optimum, we can prove that a non-monotone submodular function becomes monotone when restricted to the local optimum. Roughly, this is the idea. So then we can apply known mechanisms for monotone submodular functions. Well, I'm saying roughly because eventually things do not work out as nicely. So what is a local optimum here? So since we're looking for a set to maximize evaluation function, the most natural definition of a local optimum is to say that V of s delete I for any item I is known higher than V of s, and V of s union I is also at most V of s. Okay? Suppose that we manage to find a local optimum. Say S is a local optimum here. Because we are in the context of symmetric submodular functions, that means that A delete S is also a local optimum. Okay, so if you find one local optimum, actually you get two of them. Okay, so what? Is this helping in any way? Let's see how it helps. First of all, we can prove the following simple fact, that the budgeted optimal solution on either this or the other local optimum is at least half the budgeted optimal on the whole set of items. Okay? So that's actually a simple fact based on the submodularity of the evaluation functions. But the more interesting thing is this monotonicity lemma. If V is submodular and S is a local optimum, then the restriction of V on the local optimum is non-decreasing. So V becomes monotone within S and within A delete S. Okay? So that means that in order to proceed now, so suppose that we identify a local optimum, the second phase of the algorithm would be to just use one of the known algorithms for monotone submodular functions. In particular, we can use the algorithm of Svyridenko from 2004, which gives an E over E minus 1 approximation, plus the two factor that we lose from the two local optima, so that way we could get a 2E over E minus 1. Okay. So this is the approach. And we're hoping that this would work out nicely, but, well, there are some technicalities. First of all, we cannot always find local optima in polynomial time. Okay? Maybe this process needs to run for a long time. So that's the first problem. Well, this can be taken care of quite easily because we can resort to approximate local optima. This is quite common. People who have worked on local search, that's what they do all the time. So this can be solved. So what, in order to ensure polynomial running time, we can shoot for a 1 plus epsilon over n squared local optima. So let's say that S is a 1 plus epsilon approximate local optimum when we replace 1 here by 1 plus epsilon, okay? So it's not an exact local optimum, but you're close to being a local optimum. Okay, so, and this algorithm by Feige, Mirokny, and Vondrak identifies in polynomial time a 1 plus epsilon over n squared local optimum, okay? Okay, so we can fix this issue, but now we have problems because, sure, we can find an approximate local optimum, but we needed the monotonicity lemma before in order to be able to apply known results for monotone submodular functions. Once we go for an approximate local optimum, the monotonicity lemma may not hold anymore. Okay, so we run into a second problem now. Without the monotonicity lemma, we cannot use any known result. Okay, so we don't know what to do. Fortunately, there is a fix for that. As we realized, the monotonicity lemma, okay, it doesn't hold as I presented, but it almost holds. What do I mean by that? I mean that the restriction of V on an approximate local optimum is not monotone anymore, but it will not decrease by too much. And the quantification that we managed to get, and that was useful for our analysis, is the following. So suppose that I denote by opt of x comma b the optimal solution under when x is the total set of items and b is your budget. Okay. So the monotonicity property that we managed to obtain is the following. Suppose that you have a set S which is a 1 plus epsilon over 4n squared approximate local optimum. Then we can show that if you take your function v and you restrict it on the two local optima on S and A delete S, then, okay, you cannot prove that this is greater than or equal to 0. That would be monotonicity. But you can prove that this difference will always be greater than minus some small quantity. And this is good enough for us for continuing our analysis. Okay? So even though you don't have monotonicity, you have some approximation to monotonicity. Okay. So let's say that we have fixed, kind of fixed this problem as well. But we're still not done because, okay, sure, we got an approximate monotonicity, but if we want to use, for example, the algorithm of Svyridenko, which works for monotone algorithm, for monotone submodular functions, we cannot do it with approximate monotonicity. Okay, so Svyridenko's algorithm needs evaluation function that is monotone within the set of items that it is defined on. The good thing is that we can do a simple modification to this algorithm, which actually remains robust under these relaxed versions of monotonicity. Okay? So with all this together, we can get our algorithmic result. So eventually we had to go and produce little fixes here and there, But eventually, by doing these approximations, by using approximate local optima and the approximate monotonicity property, we were able to get this 2e over e minus 1 approximation. Okay, so this was the algorithmic approach. Now, how do we convert this to a mechanism? Okay, so we want eventually to get truthful mechanisms. I won't go into too much detail here, but the problem is that if we want to get a mechanism, we want to get an algorithm which satisfies a different monotonicity property, which says that, in particular, we need algorithms that have the following property. If someone is accepted by the algorithm by reporting a cost Ci, then this guy should be accepted if he reports a lower cost. Well, this property, this is Meyerson's lemma, essentially. So this property actually does not hold for the algorithm I presented. So we're into problems again. What we do, how we fix this? Well, we have to use, eventually we use alternative greedy algorithms. So we still start with an approximate local optimum. So our mechanisms also start by producing an approximate local optimum. And then we run a different greedy algorithm on the two approximate local optima, on S and A delete S. The problem is that this in general leads to exponential algorithms. As I said, most algorithms known for these problems were exponential anyway. So here we will also get in general exponential algorithms for an arbitrary symmetric submodular function. Because these greedy algorithms at some point they need to compare certain solutions with the optimal solution of some subproblems. But we can get away in certain cases, like for the max cut problem, even for the weighted version, we can get away with that if we can have good LP relaxations. If we can have LP relaxations that can be solved in polynomial time, and we can bound the integrality gap, then we're back to business. Sure. So for the case of max cut, for example, what we can do is that essentially we replace this step by comparing with the fractional optimal, and by analyzing the integrality gap of an appropriate LP relaxation for max cut, we are able to get a 10 approximation, essentially. So the analysis actually is interesting. It's done through the technique of pipage rounding. And it shows an integrality gap of 4, and together with the rest of the approximations we've done with the approximate local optima, this translates eventually into a 10 approximation. Okay, so let me summarize here. As you saw from these numbers, almost all the results that we have, and the results that other papers also had in this context, are not tight. We haven't managed to obtain any good impossibility results here. The lower bounds that we have are like 1 plus root 2, like 2 point something. Okay, but at least we were able to bring down the approximation factors to, to just 2 digits. There are no results for deterministic mechanisms for general XOS objectives. We only know randomized mechanisms. And also it is not known whether there exists constant approximation for subadditive valuation functions. Okay, so thank you.
Questions? Okay, thanks.
Thank you.
So one announcement. So the vehicles for the hotel will leave after 7:30. So you have time until 7:30. And also a reminder, there's a poster session that's going to be held on the other side of the hall.
Yeah, before that we'll have this session of like short 3-minute talks to complement the poster session. These are just very brief talks, so I mean, unless the questions are critical, maybe you can just address them during the session. And yeah, I'll ask the speakers of the all the poster session presenters to sort of follow the order in which you're listed on the web page, on the accepted posters page. So I think all the PDFs are with me. I'll just, one after the other, we'll just kind of try to, we are already slightly behind schedule, so we'll follow this 3-minute rule strictly now. No, we have a single, this is your laptop or what? This is your talk, right? Yeah. Okay. So I'll have those sheets with me. I'll point you at like 2 minutes and 1 minute. And stand up when it's 1 minute.
Okay, good evening everyone. My topic is on influence maximization and revenue optimization in apparel industry. Jointly worked with Professor Manoj and Professor Mona Lisa. This is the overview of my presentation. So, based on the sessions before, we all know why we need to go social. The main point here I focus is it will not only help for advertising, it will also help for propagating the information. So why I choose apparel industry is it comes under these non-monotonic products. Okay, like for small explanation, like if more of our friends are having the similar product, then we will not be interested in having the same product. That comes in this non-monotonic function. The main motivation is like as the number of people increasing for this online shopping. These are some of the literature. So the main problem is how to maximize the influence and then revenue using these social networks. So this is the gist of solution approach. Here the main thing is the value of the product, like how many friends do we have and how many of them has already opted this product. So that we will be using with some function, so it will be giving the value of the product. This I can discuss in the poster if you meet me later. So this is the approach, greedy discount approach. So I will be going with some example for this. So this is the sample network that just for explanation I have chosen. So if it is a real world network, so first we will be sorting out the nodes in their order of degrees. So here the intensity of color shows the degree of the nodes. So first we will find N1 users in the range who will have the maximum, who will influence most of their friends. So while considering this non-monotonic function, based on that we will be choosing particular users who will have less number of friends who have opted that product. So initially everyone will be at 0, so after their friends get influenced, after their friends purchase the product, these are the different influence levels of the nodes. So when we see this range, for the next iteration, for these number of people we will be giving product for free, and then so then we will be choosing some range where we will choose less number of people and they will be maximizing more. Okay. So they will be influencing their friends. So we can see in iteration 1 we had 70 users and iteration 2 we have 170 users. Okay.
Hello, my name is Georgios, and I'm a PhD student at the University of Liverpool. I'm going to present to you a poster titled Mutants and Residents with Different Connection Graphs in the Moran Process. This work will appear in LAT in 2018, and it's co-authored by Nikoletsas, Raptopoulos, and Spirakis. So what we have done is we have generalized an already existing process, which is called Moran process, which aims to model the spread of mutation in biological networks, or the spread of ideas in social networks, or the spread of malware in computer networks. So the process goes as follows. We initially have a set of nodes, and a node can have a type, so it has one of two types, either a resident or a mutant, and the type determines the reproductive success of the reproductive rate of a node, which we call relative fitness, and also the neighbors of the node. So the process goes as follows. Initially, everyone is a resident, except for one, which is picked to be a mutant uniformly at random. And then in each time step, a node is randomly chosen with probability proportional to its relative fitness, and it reproduces with equal probability to one of its neighbors. Now, so if a resident reproduces on a resident, then nothing changes. But if a mutant reproduces on a resident, then the graph changes. And this process goes on until one of two outcomes are reached. It's reached, sorry. So either fixation is reached, where everyone is a mutant with probability f, which is called the fixation probability, or extinction with probability 1 minus f, where everyone is a resident. So we can see this as a bimatrix game, where the players are a resident and a mutant. Their actions are all strongly connected digraphs, and the payoffs are extinction and fixation probability, respectively. So our main question is, what are the pureness equilibria in this game, if any? So is there any pair of digraphs such that neither the resident or the mutant nor the mutant wants to deviate from it unilaterally? So now our results focus on the fixation probability, of course. So we need to find out what the payoffs are for the players. We found some lower and upper bounds for them, for general digraphs. And then we focus on the case where one of the graphs is the complete graph. We found some upper and lower bounds on the fixation probability, and our results indicate that the best response for every player is the complete graph. And we also provide a fully polynomial randomized approximation scheme for the problem of computing the fixation probability when the mutant graph is the complete and the resident graph is an arbitrary undirected. Yes, an arbitrary undirected graph. You can find the full version of the paper on arXiv. Thank you very much.
Okay, hi everyone. So in this work, we consider a variant of resource allocation problems. So in typical resource allocation problems, we divide a set of resources among interested agents. So the agents are inherently in conflict with one another. Whereas here, all of the agents belong to the same group, and they're going to be allocated the same subset of items. Our goal is to make this subset agreeable to all agents, where you can think of agreeability as a minimal desirability condition. So some agents might prefer other subsets to the allocated set, but all agents think that the allocated set is at least acceptable, and they can all agree with this allocation to the group. Now, without further constraints, the problem I described so far would be trivial. Right? Since there's only one group, we can just allocate the whole set of items to the group. And so we impose a constraint on the size of the allocated set. So we want the set to be as small as possible. Okay, so what are some applications of this setting? Well, you could imagine that the agents are going together on a trip, but they share only one luggage, which has limited space. And so they have to agree on which subset of items to put in the luggage. So here, agreeability says that all agents should like the set of items in the luggage at least as much as the complement set of items left at home. Or in other words, based on the set of items, no agent would rather stay home than go on the trip. Another example is that the agents are receiving some items in a resource allocation setting where there are also other groups, but the preferences of the other groups are either not known or are given lower priority. So maybe the other groups haven't arrived, or they're placed lower in a team competition, and so we want the allocated set to be agreeable to the first group while leaving as many items as possible to the remaining groups. And so if we allocate items between two groups, agreeability says that no agent would rather switch from the first group to the second group. So in this work, we consider the question of how well we can approximate the size of the smallest agreeable set in polynomial time. And for this, we consider three well-known models for representing preferences, namely ordinal preferences on single items, where each agent just submits a ranking over the items, general preferences, where the agents can have arbitrary preferences over subsets of items, and additive valuations. And for each model, we established tight bounds on the approximation ratio of algorithms that run in polynomial time. And I look forward to seeing you at the poster. Thanks.
Hello everyone, so my name is Soprava, and I'm going to present our work on surprise in elections. This is a joint work with Palash De and Pravesh Kothari. Given that recent times we have seen lots of surprising, perhaps shocking election outcomes, we tend to ask the question, what is the role of the social network formation and people's local observation on this event of surprise? And our work starts with the following observations, that voters generally build estimates of the distribution of preferences of the whole population based on their local neighborhoods, whatever feed we see in our Facebook pages and so on, and also the estimates of their social connection probability. So it's more likely that if I am a red node, I am more likely to be connected to a red node than a blue node, and things of that sort. And this issue is more grave in the age of social media, because in social media we typically have a lot of friends, and somehow we tend to believe that our local observation is kind of representative of the global observation, global state. And we define surprise as the probability that my perceived winner, so I have now described what is my perceived. Suppose I perceive a winner depending on my personal observations. When that is not equal to the true winner, I get surprised, and we just call the probability of that event as surprise. And the approach that we take is we build a model which is essentially a stochastic block model. So this is a general version of the Erdo-Shreni model, where you have different probability of connection between a different class of nodes in a graph. And these connection probabilities are biased by the preferences of those individuals. So if both of these individuals have the similar preferences, then you are more likely to be connected to them than someone having a dissimilar preference. And so the voters also estimate. So we assume a model for that voters estimates. And this implicitly is a combination. So one specific example, what we did in the experiment section, is an implicit combination of media reports and their personal observations. And the results that we show are essentially attest the fact that surprise occurs when there is a discrepancy between your estimated bias and the true bias in the local connection, and whenever this exceeds a certain threshold. So I would be happy to elaborate that in my poster session. And another interesting fact that is coming out of our results is that surprise is a phenomena of a closely contested election. So if there is a landslide victory for one agent, one candidate than the other, then it's very unlikely that anybody will be ever surprised. And then we go to the setting with more than 2 candidates and look at different standard voting rules and evaluate their performance based on this metric called surprise. And we kind of, in this 3 candidate case, we kind of see a kind of a negative result, which says that it is unlikely that we'll get a single voting rule which will be less surprising for all parts of the population. So that's one thing. And then finally, we look at the Brexit dataset, experiment with a Brexit dataset, and essentially see that some of our theoretical predictions are indeed true in practice. So, yeah. Barely? No. So it's just that. So whenever the margin is like half plus epsilon and half minus epsilon, then this problem is very prominent. Otherwise, it's not. Yeah. Okay. Thank you, and see you in the poster session.
So, hello everyone. I am an undergraduate student at Indian Statistical Institute. I'll be talking about combinatorial auction for particular case. I tried to give a proposal for the combinatorial mechanism for particular case. So it is for IPL player auction. So basically IPL is a T20 cricket league. You can see as a football cricket league, a football league. So it was set up in 2007 by BCCI. So auction is put up for formation of teams. So and the mechanism they use is sequential single item English auction, which is distort the valuation of complementary resources, and also for the budget constraint it is very difficult for the bidders to estimate how much they should bid. Actually the sequence is random, so they don't know how, if a player comes on the later on part, then he will get some less money because of the budget constraint. So these are the problems in the current auction mechanism. So I am proposing a combinatorial auctions bidder in which the bidder can bid on pair of players or single players, so reduce the complementarity constraint. Because the computational complexity of winner determination this is a NP hard problem, and in case of cricket, the players complement each other as in pair of players, because only pair of players are involved. If you talk about batsmen, only 2 batsmen are playing, or pair of fast bowlers. So I put an assumption on complementarity. So in other it is combinatorial auction is also difficult because bidder has to evaluate exponential many bundles. Okay. So here is the proposed auction mechanism. So bidder can bid on pair of single player or pair of players. We have fixed the budget, avoid the domination. So auctioneer start with some reserve price, and he will update the reserve price after each round. So auction dynamics, I have simulated the auctions using 6 bidder and 25 players. Actually, I simulated for 500 times. So this is the dynamics. Auctioneer announces the initial reserve price, bidder generates their bidding bundles, optimal bidding bundles using those reserve price, then they will submit their bid, auctioneer will solve the winning determination problem, players allocated, temporary allocation happens. If now I'll check if stopping condition satisfies, stop the auction, otherwise auctioneer update the reserve price, then this loop will go on until the stopping condition satisfies. So some results that we got revenue higher in revenue and social welfare higher in all the simulations uniformly. Numbers are 19.2%, social welfare were 19.2% higher, and social welfare was 17.5% higher, and revenue was 19.2% higher. So yeah, that's it. Approximate 35% of simulation we got the maximum possible social welfare. So I have no explanation, mathematical explanation for it. So yeah, you can visit my poster if you have.
Yeah, this is a PDF that was sent to me.
Yeah, can I do the PPT now?
Maybe you can just take to this. I don't want to spend time changing things. I'm sorry. Or you go ahead. Let's go at the end. Maybe you can do at the end of the session. Yes. We kind of, for technical reasons, skip a talk, and so. Yeah, you should have told me this. Yeah, so I'll tell you that it's 2 minutes.
Good evening, everybody. It's my pleasure to present our work at here, which is recently published in a journal named Journal of Business Research. Why need to predict consumer purchase intention? To float effective online advertising or recommendation to the customer, and these are. Why digital platform and Amazon? In the year of 2016, e-retailer have generated estimated at 1.9 trillion US dollar from 1.61 billion customers globally, and Amazon has more than 310 million active customer account who brought near 136 million US dollar goods in 2016. Why durable goods? Approximately 34% durables would consumer purchase from total online market. Why consumer review? Here I am highlighting that Amazon has increased their revenue up to $2.7 million after setting the question, why is this review helpful to you on each customer review records. This is the published paper relevant area, and this is the proposed case scenario. We divided the case search to purchase into 4 separate parts. One is the search attributes to choice, like people can search sensor attribute CCD and finally choose CCD. And one is view attribute review to choose, like picture polarity is 0.11 and finally choosing a 0.10. And another case, people may search attribute and looking corresponding product overall review and choose, like pixel first search 10 and product polarity look 0.11 and finally choosing pixel 12.2 and 0.117. Another condition, people can search attribute with screening that particular attribute review, like they search Kodak brand and corresponding brand polarity 0.11 and finally chosen Nikon and corresponding polarity 0.11. And finally, they are taking in this model, they are taking this purchase attribute value and searching that which products are relevant and to those attribute value, and found that these two products are relevant, like here 12.1 megapixel, here is 12.2, like nearest about that. And after selecting those products, you can give recommendation or advertising to the customer. This is the methodology used. Sentimental is used to classify the text into positive, negative and neutral polarity, and social network mining is applied to find out the project quality score. And here two regression analysis is used, nonlinear and linear regression, to find out that which attribute follow linearity and which attribute not follow nonlinearity. This is the prediction graph. This search is divided into 10 decile and find that which attribute is most profilable in which decile, like display consumer initially they didn't search display, but middle they search display. This is the result, and this is the manager insight, like consumer doesn't bother about available review of the attributes and seller. Another one is that consumer can compromise their budget if they are satisfied with the search durable goods. And this is the inconsist checking, the conclusion, and this paper is published recently.
So, okay, this work is about differential pricing of content in the internet. So, this is joint work with my student Shashank Mishra and my collaborator Ezekiel Ayel. So, there are several topics discussed in the net neutrality debate. These topics can be broadly classified topics under technical aspects and economical aspects. Under technical aspects, the topics discussed are whether discrimination of packets or throttling and blocking of traffic should be allowed in the internet, or what kind of quality of service should be guaranteed in the internet. On the economical aspects, things discussed are whether exclusive agreements and side payments and differential pricing should be allowed in the internet. So, what we focused in this paper is about the study of the differential pricing. So, the differential pricing says that in the differential pricing, you will be allowed to charge data access based on from where you are trying to access the content from. Some of the examples of differential pricing are the zero rated platforms like Airtel Zero or Deezer or Bing on video streaming. So, when you access traffic content from this platform, your data access is not charged. If you access data from somewhere, your data access will be charged. So, there are several regulations and discussion going on this in general net neutrality topic. Till recently, FCC has banned this or put some restrictions on this differential pricing scheme, but a couple of days back, this has been refilled. So, differential pricing is legal as of now in US, but this practice is banned in India as of now. So far in the net neutrality debate, the focus has been on ISP. The argument was like, okay, these ISPs are not investing enough in the infrastructure, but they want to make more profit out of it. But this same question can be asked about the content provider as well. Is the content provider are investing enough, and but are they investing enough? To understand this, we consider this simple model where there is an ISP which connects the user at one end with the content providers on the other end. So here ISP is like a top player which is going to set up the prices, and content providers the one who are going to decide the sponsorship and non-sponsorship decisions. So the sponsorship decision is where they are going to say whether I'm going to subsidize your access price. So this is the decision of the content provider, and we model the user simply as the ones who generate demand according to some Poisson process. So this turns out to be a simple non-atomic game, and we can analyze this game and try out how the users spread their traffic across various content providers. So the basic questions we asked in this paper are, is it possible that under differential pricing scheme, there is an unfair distribution of the revenues across the content provider, and is it possible that under differential pricing scheme, the users end up having a degraded quality of services? So in our paper and our analysis showed that yes, this is possible in differential pricing. A content provider with poor quality of service may end up earning higher revenue, and also under differential pricing, it may happen that the quality of the service, for the quality of service in particular, the mean delay can be very bad for the user. So as to overcome this, we kind of propose this following policy recommendation. Yes, the differential pricing should be regulated, it should not be made totally legal, and the way it should be regulated is content provider which offer higher quality of service should be allowed to offer higher subsidy. Okay, that's all. Thank you.
Good evening everyone. Myself Shankar Kumar Mridha from IIT Shivpur. My presentation topic is Dutch auction is suitable for competitive crowdsourcing market. So first I discuss about some crowdsourcing. So crowdsourcing is basically online distributed public problem solving process where a group of workers basically solve a problem. So in my presentation we basically consider as the crowdsourcing platform is basically competitive crowdsourcing platform where decomposable tasks can be solved by the crowd worker. So in competitive crowdsourcing market, basically workers are submitted their solution with their bid value is like a Dutch auction. So what is the Dutch auction? Dutch auction is the open price auction policy where a auctioneer set a higher bid value at the starting of the auction, and during the auction they basically decrease their bid value until some of the bidder can accept that bid. So in Dutch auction, if we apply our Dutch auction in a competitive processing market where the tax is basically decomposed into multiple sub taxes. So if the tax is decomposed into single subtax, then a single worker can be good for this case. But in the case of a decomposable tax, the tax is basically submitted into decomposed into multiple subtaxes. So as a result, a worker never find some propose the best bid value for every taxes. So if you consider in this picture where a requester basically posted tax which is decomposed into exactly two subtaxes. Here, if we consider that the single winner basically win this tax, then the WC3 worker or W5 or W3 worker or the W5 worker can be win in this tax. But that solution is not good for this good for the worker, because if the worker combine the solution, then that is best for this best for the requester. If we consider that if the W1 worker and W2 worker are basically collaborate to each other, then they can minimize their bid value compared to the worker 3 and worker 4. So from this case, we just choose a theoretical lemma. That lemma is basically says that the minimum bidder W3 in Dutch auction has a following winning probability if the bidder if the two nearest bidders are allowed to collaborate to each other when the tax is two non-empty decomposable. So the winning probability for the minimum bidder is greater than half in this case of time variant cases, and is less than equal to half for time invariant case. So time invariant case means the worker are we just see when the worker basically posted the solution, the time also considered in that case. But in case of time invariant, if the two worker post the same bid value, then both the workers basically win in this task. So that is our lemma. That lemma is basically shows that in case of time invariant case, the minimum bidder never collaborate to each other, but in case of time variant case, the worker are not interested to collaborate to each other. So the worker our main aim is to create some mechanism that can encourage the minimum bidder to further collaborate into the system. So that's overall presentation is. So thank you.
Yeah, so I'm audible. So topic is extending partial functions, and this is joint work with my advisor Umang Bhaskar. Yeah, so we consider two problems. One is extension problem. So here like partial function is given as an input, and we need to determine if it can be extended to a function with some property. For example, this is a partial function from power set of 3 to real number. So question is, can we fill the remaining entries so that the new function, total function has some property. And the property which are of interest are, which we have considered are coverage function, submodular, convexity, matroid rank. And second problem is oracle construction. So here we assume that the partial function is extendable, and we want to find any one extension. So what is the motivation behind this this study? So one is like one motivation is from game theory. Like we want to test whether the real life data on utility functions satisfy the assumed property or not. For example, most common is submodularity. In some cases, linear. So we want to test whether that is true or not. So data we can get from like multi-item auction. Like there are many items and bidder bids for several subsets of item. So basically we have several subsets of item and corresponding bid, that is utility. And if this utility is truly submodular, then there must exist an extension. So this is the problem. So another motivation is on property testing, and you can see poster for more details. Okay, so let us come to convex function. So what the problem looks like for convex function. So here input is like n points in Rm and the corresponding values. And the question is, does there exist a convex function which passes through this point? So basically we proved that this is in polynomial time solvable, and the main idea is convex roof. So what is convex roof? It is the like maximal convex function such that FTI is less than or equal to Fi for all I. So there are two examples in one dimension. So these are the T1, F1 are partial function. So T2, F2, and this is a convex roof. So so basically we have theorem that partial function is extendable if and only if convex roof value equals Fi at each Ti. So which is case in this case, like however in this case, like at T2, function value is strictly less than F2. So we can show that this is not extendable. And convex roof can be efficiently computed. So therefore this problem is polynomial time solvable. So basically this was one of the results, like convex function extension problem in P. So we have shown that oracle construction NP hard. So next we consider submodular function. So here we have result that when the input set size is small, like order log m, then it is polynomial time solvable. And when the input forms an anti-chain, then it is always extendable to a submodular function. So one open problem is like we don't know what is the complexity when the input set size can be arbitrary, like not small, can be anything. And for coverage matroid, we proved that extension is NP hard.
Good evening all. I will be talking about how to compute equilibrium in atomic splittable routing games. Yeah, so as we saw in yesterday, so these routing games are useful for modeling different kinds of network, traffic networks, data network, and different kinds. So consider example. So consider this example, like they are from source to destination. There are two parts. One is like a broad expressway where like independent of number of cars, every car takes like 1 hour. And another is a short part but which is congestion, and every car takes how many cars are on the edge. Yeah, for example, if we take the 100 cars in a network, then we can see that if 40 cars go on top edge and 60 cars go on second edge, then every car takes 60 minutes and it's equilibrium. Now we consider atomic splittable routing games, like where like the player have a significant effect on the network. So for example, there are two freight companies or car companies where red color wants to send 50 cars and blue color sends 100 cards. So this one of the possible strategies for these players. So red company sends 20 cards from top edge and 30 cards from second edge, and similarly for blue card. Now if we take the time taken, which is cost for the players, like we can compute the total time taken is for red company statistic. These are the numbers. Now if you see this is another strategy, which one of the another strategy, and it can be computed that this strategy is the equilibrium. Like unilaterally, none of them can change the strategy to decrease their cost. Now coming to history, like the existence of equilibrium in these kind of games is first shown by Rosen in 1965. Now coming to computation part, like till now we only know how to compute efficiently if either all the cost functions are linear or if all the players are symmetric. In a sense, like they send from same source to same destination, they want to send same amount of demand. Now coming to our results, we showed that like if we consider a network with parallel edge graphs with convex cost functions, we can compute the equilibrium, and we can compute in polynomial time if either number of edges is small or if the number of players are small. And also we showed that like it's NP, like in a general atomic spiritual routing game, like it's NP hard to determine if there exists a player with cost at least C at some equilibrium. And the idea is like we reduce using subset sum problem. Now coming to our algorithm, like we have a sorry, time's up. So just coming to idea, like we have marginal latencies which are derivatives on the cost of edges. Then like we say that we have a result that at equilibrium the players use only those parts where their marginal latencies are minimum, and we try to use this result to find our equilibrium.
So good evening everyone. I'll be talking on in the graduating bits of this poster session. So my research topic is on judgment analysis based on crowdsourced opinions. So let's suppose to start with an example. Let's suppose that one person is asking a question that showing my son Disney Aladdin would not make him to join in military service, will it? So he can outsource this question to crowd, or by posting it in any social media, and get public opinion over it. So let's suppose that there are three possible options: skip, yes, and no. So according to the majority voting, no will be the final answer. So judgment analysis is basically a general way of learning about human decision from multiple opinions. So in the context of judgment analysis, in the left hand side you can see this, there is a response matrix where the annotators are in row wise and questions are in column wise, and the cell value denotes the opinions of annotators over some questions. So here there are 5 opinions, there are yes, no, skip, unsure, I can't tell, etc. And on the right hand side you can see there is a judgment matrix, and here row wise there are some questions, and column wise there are some options. Here as this response matrix there are 5 options, therefore in this judgment matrix there will be 5 options, and the cell value denotes the weight of a particular option, for a particular question. So the maximum cell value, maximum weight of a particular question will be the final answer. So here you can see that in the response matrix for question 1 there are multiple opinions, yes, no, yes and I can't tell. So according what will be the final aggregated answer from these multiple options. So according to the majority voting, yes will be the final answer. But in crowdsourced setting, as there are some lot of challenges like existence of spammers and inclusion of noise, therefore majority voting cannot be reliable. Therefore we need some, our goal is to find out more sophisticated design to find out the aggregated judgment from multiple noisy opinions. So in my work, there are mainly 4 contributions. That is a biclustering based approach for crowd judgment analysis, and this is mainly for independent crowd judgment analysis. Again, we have used, proposed another PGM model, that is probabilistic graphical model, considering annotator accuracy, biasness, and question difficulty. And whatever the model I have discussed so far, it's basically independent crowd opinion. But there in real life, you can see there are so many options. There are so many real life problems where one annotator can see others' opinion before posting his opinion. So this includes some biasness when he's giving his own opinion. So we are considering, we are introducing this new type of judgment analysis model, and we are mentioning it as dependent judgment analysis model. And again, we have introduced another new paradigm of judgment analysis. This is called constraint judgment analysis. The main difference in normal judgment analysis, the response matrix in this question posted in this judgment setting are basically can have a single component. That is, one question can have only one answer, yes, no, and sure. But in this constraint case, it has multiple components. So how to aggregate it will be more challenging how to aggregate the final decision. And there will be some applications, and it will be better to discuss in the poster sessions. And these are some references. This of my few recent publications, and I'm looking for some postdoc options. So if you are hiring, so please let me know. Thank you.
So good evening all. I'll be talking about Shapley value based binary classifiers. A recent White House report suggested that major issues with large scale data is a lack of transparency. So zooming into classification, this can be related to fairness of a classifier, and we intend to address this problem using cooperative games. As most of you might be knowing that the combination of game theory and machine learning has already been existing in areas such as feature selection and designing sparse classifiers, identification of feature influence, etc. But still, why binary classification to game model? So consider an example of an ad placement on a web page, say top or bottom, with different costs to be incurred by the advertisement owner. So the goal here is to predict where to place the advertisement with minimum error using historical data. To solve such problems, one can ask for a linear classifier given interacting dependent factors or features here, that is xi, and the corresponding labels yi. So we want to identify a classifier which has total training apportioned close to the Shapley value based apportionment, Shapley value based fair apportionment. In this direction, we design a TU cooperative game with features as players. The characteristic function uses hinge loss, which is a popular loss function in classification. So for a two-player coalition, the characteristic function is basically the minimum training error incurred when only two features are used for classification. Next, to design a classifier which incorporates the requirement of fairness, we follow the procedure given here. Step 1 is to compute the characteristic function, step 2 computes the Shapley value, and finally step 3 involves solving an optimization problem which basically minimizes the sum of deviations between Shapley value and the training error due to the proposed classifier. We have different variants in this. One point to note here is that unlike SVM benchmark algorithm in classification, we do not use Tikhonov regularization. To validate our model, we have we have performed some initial computation on a couple of small data sets. As can be clearly seen from the figure, our models have comparable CV error to that of SVM, that is in green, but suggesting that some implicit regularization is being performed. But as all good things come with a price, due to the combinatorial nature of Shapley value, we have scalability issues and we are trying to work around it. Finally, to conclude, we propose a game model for binary classification with features as players, and design a fair binary classifier which is observed to have implicit regularization property. Thank you, and all of you are welcome for the poster.
Okay, so this is joint work with Eftichia Vakaliou, who is an undergrad student in my department, Georgios Amanatidis doing a postdoc at CWI, some people from the Liverpool group, George Christodoulou and John Fernley, and Christos Alexandros Psomas who is doing a postdoc at CMU. Okay, so it involves cake cutting. Some of you were here at my tutorial yesterday, so maybe a couple of these slides will be familiar to you. So we have a set of resources which we want to allocate to a bunch of people. The goal is to divide the resources in a fair manner. And the problem is, of course, ancient, but from a mathematical point of view, the first publication started appearing in the 40s, focusing on the objective of producing proportional allocations, and ever since there has been a rich literature. So the resources are usually represented by the interval from 0 to 1, and we have a set of n agents, and we assume that the valuation functions are probability measures on the interval 0, 1. So the access to the valuation functions, we assume that happens through evaluation and cut queries. So a value query is just asking a player for his value for a subset of 0, 1. A cut query asks an agent to produce a piece of a certain value. Okay? So there is an interesting history about this problem. There are various, so the objective here is to produce an envy-free allocation, meaning that we want an allocation such that nobody envies any other agent. There are various proofs of existence, but in terms of algorithms, it's a very bizarre situation. Up to 3 agents, the problem is trivial. For 4 agents, it was an open problem up until last year. And last year, there was the first algorithm that was proposed, requiring about 600 queries. And for general N, the current complexity is astronomically high. So what we have done so far is that we have an improved algorithm for the case of 4 agents. Our improvement, it achieves an improvement of more than a factor of 2. We get it down to around 260 queries. We are making a lot of use of the building blocks that were there in the Aziz Mackenzie paper, on the paper for 4 agents. But we are adding some new insights, and we managed to simplify several steps. And the high-level approach is that, as with any other algorithm on cake cutting, we start from an empty allocation, and we keep building up a partial envy-free allocation and some residue. We keep diminishing the residue until we are left with the empty set. If we want to take a closer look, what we're trying to establish here is domination relations throughout the algorithm. So an agent I dominates an agent J at a given point if allocating the rest of the cake, the residue, to agent J does not create envy for agent I. So that means that for this pair of agents, I and J, I don't need to worry about the possibility of I envying J. So by trying to create more and more dominations, that means that we care less and less about certain pairs of agents, and this allows us to produce a better and better allocation up until the residue becomes the empty set. Okay, so more details in the poster.
Hi everyone. So I'll be presenting a bit of work with a student, Ida, who was one of our summer interns at EPFL last year and is now a PhD student there. So here we looked at a model for information networks, a game theoretic model, where the idea was that we wanted to look at a model that captures how information can be propagated in a network, things like Twitter where you can follow someone, right? So each node is an agent, and it is up to them to decide which edges, which directed edges they want in this network. And of course there's a trade-off. So there's a trade-off between the cost of maintaining this follow, but you get some reward, which is via short paths to other agents. In particular, any path of length at most k, we're going to count as having some value for that agent. So if we let C be the cost of one of these directed edges, and RKU is the number of nodes that are reachable from U by a path of length at most k, given everyone's structure, everyone's choice of edges in this network, then we say that the utility for this agent is exactly, sorry, I don't have a pointer, exactly this number of nodes that we can connect to minus the cost for the number of edges that we were building. So there's many similar models like this, probably one of the most famous ones by Bal and Goyal in 2000, which basically looks at this with k being infinity, so anything that is reachable. There's many other variations. So given this model, one can first ask, what are efficient networks if we're talking about social utility? So if you want to look at a Nash equilibria that is efficient, we can show pretty easily that the best network is this type of flower graph, where these petals are of length k over 2, and you have one central node that basically connects to each petal, and in this form, when you build it together like this, every node is reachable from every other node. If you want to impose some kind of symmetry argument, you also have efficient, stable efficient graphs where everyone has, say, 2 edges for the right values, for a range of values of C and K. So the real question here is, okay, you can build these kind of networks, and a lot of work had been done on these other models where you get such structures, but what we really wanted to look at were some nice dynamics that converge to some real-world networks, something that we might see in some of these information networks. So if you look at the best response dynamics, you quickly see that you only get things like cycles or not very interesting networks. Instead, we looked at a very simple dynamics where we just consider one edge at a time. We look at one possible connection and we see, can we add it? Does that improve our utility? Or should we remove it? Does that improve our utility? And if you look at these dynamics, what is nice is that you actually get very rich structures appearing in your networks as fixed points. So you can have things that are triangles, you can have open triangles as well, so a variety of clustering coefficients are supported as fixed points. You can have homophily, you can have heterophily, so again, in that sense, you have many different rich structures, and you can have all kinds of community cluster type networks, broadcast networks, all these types of things that you see in real life are actually fixed points of these dynamics. So that's it. Thanks.
So, good evening, everybody. So, how many of you have heard about blockchains? So, I'll give a very brief introduction about what blockchains are and what smart contracts are and what motivated us to do this product. So, basically, you can think of blockchains as a digital ledger where all the transactions between two entities are stored. So, you can think of it as a very completely decentralized and peer-to-peer network where all the transactions between two entities are stored in a cryptographically like secure fashion. So nobody can tamper with it. So what motivated us is in 2015, Ethereum generalized the blockchain technology to include something called as smart contracts. So smart contracts are just codes written which can have any logic in them. So you can think of it as a promise. So instead of saying I pay you this money, I am saying I promise to pay this much money if you deliver me something. It's kind of like saying if I'll give you $3 if you deliver a cup of coffee to me. So something like if you fulfill some conditions, then the contracts executes automatically. So this is what really, like, CoinEarth is a startup in Bangalore, and we got really excited at this idea of designing smart contracts and having our own logic which deals with use cases of mechanism design and machine learning. So one of the first use cases we worked on, and we are still working on bettering it, is using smart contracts in civic crowdfunding projects. So civic crowdfunding projects, if you just say, okay, I have a project, like I have a community park which I want to better or renovate, nobody will contribute. So we are using mechanism design to incentivize the contributors to contribute so that the project is funded. So especially we are using provision point mechanism with securities. So that actually ensures that at equilibria, if the project is actually valuable for the community, it will be funded. So now you have mechanism design, but you still need an intermediary to actually facilitate transactions between the user and the donators, or the requester and the contributors. So that is where blockchain comes in. So in blockchains, we put all the logic of mechanism design and how you disperse money and transactions in a smart contract. So the smart contract implements all this logic and everything is automated, and nobody gets to touch it because nobody gets to tamper with it, because everything is decentralized and it's a peer-to-peer network. There is no centralized intermediary in between. So there is no trust that you actually require if you want to implement any projects like this. So we built a decentralized application, or DApp as we call in blockchain technology. So we have, all you need is actually a web page which interfaces between the users and the smart contracts which are deployed in the blockchain. Now, suppose your project is funded because you have mechanism design and you're forcing the contributors to contribute and fund the project. Now the project is funded, but how do you transfer the money to the requester? Like, how can you trust that the requester will do it? So that's where oracles come in. Oracles, we used IoT oracles, which automatically measures the progress of a project, and then it interfaces with the smart contract to disburse money in proportions. So we can design any logic in this. We are still working on having mechanism design to have the logic of dispersing money. Or we can also have human oracles, like a bunch of people can actually work as oracles, nominate as oracles, and they can say what the ground truth is. And only based on that, the money will be dispersed to the requester. So that's what we have, and if you are interested or if you have any queries, you can come to the poster. Thank you.
So let's thank all the speakers one more time. So since we are running like half an hour behind schedule, the departing buses for the hotel have been pushed back. So instead of 7:30, the transportation will leave for the hotels at 8. Thanks.